Welcome to Dalton's law of partial pressures. So, John Dalton observed that the total pressure of a mixture of gases equals the sum of the pressures that each gas would exert if it were present alone. So if we take, say, this container where we have the blue molecules, we've got some pressure being exerted downwards, we've got two weights there. We have this other container, same volume, but now we have the red molecules, we have some other pressure being exerted. In this case we have five weights. If we take those two sets of molecules and add them together in the same volume container, in order to have the volume be the same, we have to take the two weights from there and the 5 weights from here and stack them up. We need 7 weights there, so you can count them. There are in fact 7 weights there. So the total pressure is the sum of this pressure plus that pressure. The total pressure being exerted, that total weight being exerted downwards, is the sum of the 2 weights added together. So this is known as Dalton's law of partial pressures, which says that the total pressure, P total, is equal to the pressure from gas 1 plus the pressure from gas 2 plus the pressure from gas 3 and so on. So each of these P sub I values is the partial pressure of the ith gas, so the first gas, the second gas, third gas, and so on, all the way up to however many gases we have. So the partial pressure is the gas that gas would exert if it were in the container alone. So basically you take all the other gas molecules out and just leave the molecules of that gas that you're interested in. What pressure would be left? That's the partial pressure of that gas. So if we assume that each gas behaves ideally, then the partial pressure of each gas can be expressed using the ideal gas law. So P1 is equal to N1 RT over B, and P2 is equal to N2 RT over B, and P3 equals N3 times RT over B, and so on, for however many components you have. And that means that the total pressure can be expressed like this. P total is equal to N1 RT over B plus N2 RT over B plus N3 RT over B. And that means, of course, we can factor out RT over B. And that gives us pressure. The total pressure is equal to N1 plus N2 plus N3 plus and so on for however many components you have, times RT over B. Well, N1 plus N2 plus N3 plus and so on for however many components you have. That's just the total number of moles, so that's N total. Well, that means that P total, the total pressure, is equal to the total number of moles times RT over V, which basically means that the whole system follows the ideal gas law, just like each individual part of the system follows the ideal gas law. So that means that if the total number of moles is all that matters, then the identity and composition of the gas particles must not matter. Because if it doesn't matter whether we have some number of moles of component A versus component B, it doesn't matter, we just have the same number of moles. That means that it doesn't matter what the identity of it is. It doesn't matter whether you have oxygen or nitrogen or helium or carbon dioxide. And that means that we can make some conclusions about what an ideal gas is or how it behaves. We can say that the volume of the individual gas particles must not be important, because the volume of different gas particles is going to be different. So if it doesn't matter the identity, then the volume of the individual gas particles must not matter. And it means that the forces amongst the particles must not be important, because different molecules will attract or repel each other to different extents. But if it doesn't matter what the identity is, then those attraction and repulsion forces must not matter. Which means that these two conclusions must be incorporated into our model of how gas molecules behave. So, one more thing we need to talk about is mole fraction. So mole fraction is the ratio of the number of moles of a given component in a mixture to the total number of moles in the mixture. So if we express that mathematically, we have either xi or chi I is equal to ni over n total, where the I here, the I subscript, is the a number corresponding to which component it is. So the first component, second component, third component, and so on. Sometimes we don't label them with numbers, sometimes we label them with the chemical formula. So O2 or N2 or CO2 or whatever. So it's the number of moles, so the mole fraction is the number of moles of the component that you're interested in divided by the total number of moles in the mixture. So Ni over N1 plus N2 plus N3 and so on, all the way up to the the last component in the mixture. So that means that from the ideal gas law, we have Ni is equal to Pi times RT over V. Well, that means that now we can take our chi I, our mole fraction, which was equal to Ni over N total, and we can replace Ni with Pi times RT over V, and N total we can replace with this expression, the P1 times RT over V plus P2 times RT over V plus P3 over times RT over V, and so on, for however many pressures you have, which means that the mole fraction is equal to the fraction of the number of moles of the component that you're interested in divided by the total number of moles, but it's also equal to the partial pressure of that component that you're interested in divided by the total pressure of the whole system. So, note that now the mole fraction, the mole ratio of a component is equivalent to the ratio of the partial pressure of that component to the total pressure. And now we can rearrange that equation to give us the partial pressure of our component is equal to the mole fraction times the total pressure in the system. So now we have a way of finding the partial pressure of a component given that we know its mole ratio and that we know the total pressure. So that was Dalton's law of partial pressures.